Hello guys, I'm here again to keep you company this evening. My name is Joseph Ejike Oji, and tonight I'll be teaching you the multiplication rules for dependent events. Yesterday, I showed you how to calculate probability of an event using the multiplication rules, and we did examples for independent events. Today we'll be concentrating on dependent events. I've already explained in my previous lecture that two events A and B are said to be dependent if and only if the occurrence of one event A affects the occurrence of the other event B. So if the one event occurrence affect the occurrence of the other event so that the outcomes or probabilities changes, then we say that they are dependent events. Good examples, for example, if A is the event parking in a no parking zone and B is an event getting a parking ticket. So the two events A and B are dependent because when you park your car in a no parking zone, you get a parking ticket. See? The same thing with having a high grades and getting a scholarship. So these are the dependent events. And tonight I'm going to show you how to calculate the probabilities of dependent event using the multiplication rules. Okay? Now let's begin. Just a brief introduction to show you the founders of the probability theory, Pierre de Fermat and Blaise Pascal, two renowned mathematicians. Anyway, just to show you, how it all started. Now, for dependent events, if two events are dependent, we use this formula to calculate their probabilities of joint occurrence. Probability of A and B equals probability of A times the probability of B given that A have occurred. Let me rephrase it. The probability that A and B will occur equals the probability that A has occurred times the probability that B will occur given that A have already occurred. This line here means given that, okay? And we can extend this formula to, any number of, actually, I wrote independent here, but it's actually dependent events. So let me, by mistake, I wrote independent here, but it's actually dependent event. So this sign here, like I said, means given that. Let me put it here. Means, okay, given that. Okay. So you can see that this symbol right here, it means given that. So now let us apply this in solving some questions. Look at this question here. It says, two cards are selected without replacing the first card from the standard deck. So I remember I mentioned in my previous lecture that selecting or sampling without replacement is also a good example of a dependent event. So when you select the card, you did not replace it. So that makes it dependent event. Find the probability of selecting a king and then selecting a queen. Now, so like I said, because you did not replace the card after the selection, that makes it event dependent. So let's see how the sample space looks for a card. Here, see, we have how many cards? There are 13 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13, 13, 13, 13, giving us 52 cards. See, we have 52 cards right here because all of them are 13s. Now, the question says, find the probability of selecting a king and then a queen. How many kings do we have? We have 1, 2, 3, 4. 4 kings and 1, 2, 3, 4. 4 queens. Now you make your selection. Before you make your selection, there are 4 kings, right? Out of 52 cards. So you have 4 out of 52 cards. Then, because you did not replace it, you now have a total of 51 cards left. Now, remember it says a king and then a queen. We have 4 queens before you made your selection. Now, even though the card is now 51 card, but still there are still 4 queens there. You see? So that's why you have 4 out of 51 cards. So when you multiply the two, 4 times 4, 16, 52 times 51, 26, 2,652. Now when you divide it with your calculator, which I'm going to show you, have I turn it on first of all, got 16 divided by 2,652. Okay, that give me 0.006. Say 0.006 right there. So now, because this is a dependent event, we use this formula here of the multiplication rule. Probability of king and queen equals the probability that king was selected times the probability that queen will be selected, given that king is already been selected. See? So that means you multiply the two probabilities. Make sense? Now let's look at another example of this. It says here, the Amica Insurance Company found that 51% of the residents of Baltimore City has homeowners insurance with the company. Remember, this is 51%. In one of my lectures, I mentioned that you can write probability as a fraction or a decimal or a percent like this. So this would be like 0.51. Of these clients, 49% also has automobile insurance with the company. If a resident is selected at random, find the probability that the resident has both homeowners insurance and automobile insurance with Amica. So in probability, we break it down step by step. This kind of question, we have 51% and 49%. Okay, I mean that give our sample space equals to 100%. Now look at this. Let us use H to represent homeowners insurance, A to represent automobile insurance. So we are looking for the probability that the person selected has both homeowners insurance and automobile insurance. Okay? Now, look at this. Let me break it down. The probability of homeowners insurance is 51%, which is 0.51. Okay? Now, the probability that a person have automobile insurance, given that the person also has homeowners insurance, is 49%. How do I know this? Because it was stated in the question that of these clients, that is, of these ones that have 51% homeowners insurance, 49 of them also has automobile insurance with Amica. So that is how I know that the probability of automobile insurance, given that they already have homeowners insurance, is 49%, which is 0.49. Now, to find the required probability that we're looking for, which is the probability that the residents have both homeowners insurance and automobile insurance, you apply the multiplication rule here. Probability of homeowners insurance and automobile insurance becomes the probability of homeowners insurance times the probability of automobile insurance, given that it has homeowners insurance, which means for this part we have it as 0.51 here, times for this part we have 0.49 times, see, that gives us 0.2499 or 24.99%. Very easy, right? I told you. Okay. Now, I know that by now that you are seeing the picture of what I mean by using a different formula, a different multiplication formula for dependent events. Now let us try another example. This will be our last example in this topic. You can try as many as you can by yourself so that you get stronger and stronger in solving. Let me put it this way, so that you get better and better when solving probability questions. It says here, 3 cards are drawn from an ordinary deck and not replaced. See? And not replaced. This is what makes it dependent. So find these probabilities. Getting 3 jacks, getting an ace, a king, and a queen in order, getting a club, a spade, and a heart in order, getting 3 clubs. So for this one, let us identify our variables here. We use J for jack, A for ace, K for king, Q for queen, S for spade, H for heart, and C for clubs. Okay? Now we're ready. It says, find the probability of getting 3 jacks. How many jacks do we have? To answer that question, we take a look at our deck of cards again. See? All the jacks here. Jack 4, 1, 2, 3, 4. 4 jacks, right? So that the probability that the first card is a jack, and the second card is a jack, and the third card is a jack is 4 out of 52. Now, before you made the selection, there are 4 jacks, right? Which is 4 out of 52 cards. Then you made the selection, and you didn't put it back, right? Now, before you make your next one, there are now 3 jacks left and 51 cards left. Then you make your selection. Because remember, you said 3 cards were selected. So before you make when you made your selection again, you didn't replace it. So this time around, how many jacks are left? 2 jacks out of 50 cards now. So this means that the probability that the first card is a jack, and the second card is a jack, and the third card is a jack is 4 over 52 times 3 over 51 times 2 over 50. When you put this in your calculator, you get this answer, okay? Okay. Now, next question is this. Of getting an ace, a king, and a queen in that order. Well, let's see how many aces we have by looking at the deck of cards again. We have 4 aces. 1, 2, 3, 4, and 4 king. 1, 2, 3, 4, 4 queen. 1, 2, 3, 4. Okay? So we're ready to answer that question. The probability of an ace and king and queen will become, we have 4 aces before you made the selection. That means 4 out of 52 cards times there are 4 kings. Now, the top one will not decline because even though you made a selection and you did not replace it, that one was for affect only the ace. It didn't affect the king. See? So there are still 4 kings, but then the card total have declined to 51. Okay, you selected. Now, you do not replace. Before your third selection, there are still 4 queen, because the one that you selected and you didn't replace affected only the king, not the queen. We still have 4 queens left, but then the total number of cards have declined to 50. So that means that the probability of ace and king and queen becomes 4/52 times 4/51 times 4/50. That gives you this answer. Okay, that makes sense? I'm sure it does. All right, next is the probability, according to the question, of getting a club, a spade, and a hat in that order. Let's see how many clubs we have. There are clubs here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 clubs, okay? And spade. How many spades? We also see a spade. You can also see that we have 13 spades. Okay, and hearts are also 13. See, hearts are also 13. So, before you make your first selection, you have 13 clubs out of 52 cards. So, 13 out of 52. Then you selected, you didn't put back. So, we now have card number, total card number of cards declined to 51, but the one you did not replace affected only the club. It didn't affect spade and heart. So we still have 13 spades out of 51 cards. Then you select. Then before you make your next selection, the card total have declined to 50, but then you still have your 13 hearts. So which means that the probability of club and spade and heart is 13/52 times 13/51 times 13/50, which gives you that. Okay? All right. Last but not the least is this one. It says 3 clubs. Now, 3 clubs, that means the first card is a club, the second card is a club, the third card is a club. So it will affect clubs only. So how many clubs do we have? Again, we have 13 clubs right here. Okay? That will lead us to probability of that the first one is a club, second one is a club, and the third one is a club is 13/52 times 13/51 times 13/50. But the problem is this. I think I have to make a correction because it affected club. So the clubs will be declining. So it's a minor error that I'm going to correct now, so that we will not get confused with that. So we have 13 clubs, 3 clubs. Let me correct it. It's gonna be 13/52 plus 12. It should be 12, not 13. 12. Then 11. Okay, and that will give us the result that we have here. Okay, let me make it big for you. So the club will decline 13/52. Then there's now 12 clubs left, which is 12 out of 51 cards, because the card have also declined to 51 since you did not replace it. Times, now there are 11 clubs left, which means 11/50. That will give us this answer here. Okay. This concludes our lecture tonight. In my next lecture, we'll be discussing the concept of conditional probability. Stay tuned and don't forget to subscribe to my channel so that you receive notifications whenever there's a new lecture available. Thank you guys. See you in my next lecture. Bye-bye.